molecular orbital theory. So short, we say MO, MO theory. And this was another Nobel Prize, 1966, for Mulliken, who was another American. And let's go ahead and get started. So I believe the first picture we're going to do are 1s. So he had this idea, again, it's orbital overlap. And we are going to see sigma and pi bonds, and sigma bonds overlap in between the nuclei, and pi bond is above and below. But what we do here is we're going to draw on the outside, we're going to draw atomic orbitals. And this is here, so we have the 1s. And then these guys come together and they make the molecular orbital. So the MO is going to be, the MO is in the middle, and the atomic orbital, I'm just going to say is AO, is on the side. All right, so the atomic orbital, when they hybridize, they're in the middle. This lower one is called a bonding MO, and the higher one is called an anti-bonding MO. Now when S's overlap, they can only make sigma orbitals. So this lower one, you don't have to write the MO there, that was just for your information. We call it the sigma 1s, and the upper one is called a sigma star 1s. So the sigma symbol, and the star stands for anti-bonding, and then the 1s is the type of the type of atomic orbitals that overlapped, and that is a subscript. And so you will have the whole thing labeled. The outer part is the atomic orbitals again, and they're just called 1s's or 2s's or 2p's. We're just going to go up through the 2p's, but you could also do it with the 3s's and the 3p's, similar idea. So this is always, we're going to only do this for diatomics. So we'll start with hydrogen as a diatomic. And so on the outside, you would have a hydrogen and a hydrogen. And hydrogens have one electron. So we'll give them each their one electron. So in H2, we're going to now have 2 electrons. And the rules are just like what we did back with atomic orbitals. So the rule that if you have 2 electrons, you're going to occupy the lowest energy. And they spin opposite directions. So we show one arrow up and one arrow down. So then we would ask questions about it. So this would be that there is one sigma bond. We haven't gotten to pi's yet. We'll do those in a minute. I'm looking at my questions are. We call this diamagnetic. And in 221, you should have learned when you talked about atomic orbitals, diamagnetic just means all electrons are paired. And so all the electrons are paired, there's not an attraction to a really strong magnetic field. There's also something called the HEMO. So I'm just going to be abbreviating this from here on out, but it stands for highest energy, occupied, and I don't spell great sometimes, so hopefully I spelled that right. And then the MO is molecular orbital. And so the highest one that we have occupied here is the sigma 1s, because we didn't get into the starred one. I'm going to talk about those in a moment. All right, so what does it mean to be, that's the idea, right? So similar like we did before, and we're going to get into the 2p's in a moment. If you have the notes, you can see that at the bottom of the page. So what does all this mean? So the bonding molecular orbital means that just like what it meant with the other theory. So in bonding molecular orbital, the orbitals overlap is between. Even with the pi bond, it's still in the area in between. It's not perfectly in between, but it's still between the so in the area between the nuclei. So like the picture on the previous page, so we're in this area is where our electrons are. antibonding, it's a very interesting idea that the electrons are not in between. So the electrons are not between the nuclei. They're actually out there. So what happens is you start filling up the antibonding. The antibonding destabilizes the bond. So down here we're in a happy zone, and then as we get higher energy, we start destabilizing. So before we go to the next step, there is something called bond order. Oh, we did this with the previous one. It's just how you calculate. It means the exact same thing, but how we calculate it is slightly different. And it is bonding electrons minus anti-bonding electrons, and then divided by 2. So subtract first. So we have 2 minus 0 divided by 2. So we'd have 2 minus 0, and then we divide by 2, so we get 1, which makes sense. So that is the formula to calculate it. You can also do it in your head really fast, just looking at the chart, because a bond is still 2 electrons. And so every time you have 2 electrons, you have a bond. So you have a sigma bond. When we start filling into the anti-bonding, they start taking away from those. What this theory allows is you can have half bonds, which in the other theory we called free radical. The valence bond theory is something that I would have worked with. So in molecular biology, biochemistry, organic chemistry, we work with models of stuff. Molecular orbital theory works wonderful because it explains semiconductors. And actually, there's a whole blurb, that book that I posted, that's a little bit older, but you can also, if you're somebody who's into that, and it allows the electrons to get excited and jump up, and it allows for doping and stuff. And so we're only going to do 2 things overlapping. There are more elaborate ones that you could look at online, or if you go to a higher class where you can have 3 things overlapping and stuff, and that's beyond my knowledge and stuff. So we're now going to do P's overlapping. So we're going to do the 2 S's and the 2 P's overlapping. All right, so 2s and 2s. So let's do this for carbon. Let's do C2. All right, so carbon, we have 2 S's, and then you want to go up higher, you have the 2 P's. So you guys have that nice little picture there. I'm going to show you where it comes from, but it's also, you're going to get to draw these at some point. So these are my 2 S's and these are my 2 P's. And these, again, on the outside are the atomic orbitals. And the atomic orbitals are going to overlap to make your molecular orbital in the middle. The number of atomic orbitals will always equal the number of molecular orbitals. So for the 2s, when they overlap, we have 2 orbitals that are overlapping, so we will have 2 molecular orbitals that overlap. When we get to the 2p, we have 3 plus 3, so there are 6 orbitals overlapping, and so we will get 6. 3 of them will be more stable, lower in energy, and 3 of them will be higher. And it always goes 2, 1, 2, 1. Yeah, I'm going to move this out a little bit so I can show my things a little bit better. And I drew it more dramatic up there. We should have 3 on each side. We're doing C2. All right, so each carbon, so this would be a carbon on this side, and this would be a carbon on this side, and in the middle will be C2. So a carbon has 4 electrons. So 2 in the 2s and 2 in the 2p that are not paired up. And now they're going to overlap. So we want to label before we start putting things in there. So this is going to be sigma and sigma star. So sigma means bonding orbital, and the star always means an antibonding. But we do want to show a subscript to say what overlapped, which is the two S's. Now, I left out the one S's. We're only going to show valence electrons. You will show me all the valence electrons, the two S's and the two P's. Yeah. All right. So when we get up here, we have the possibility of pi and sigma bonds. So when you do 2, 1, 2, 1, this is called a pi, and then the subscript 2p and a sigma 2p. Bonding orbitals are always lower in energy than the original atomic orbital. So bonding orbitals are lower in energy. So bonding MO are more stable. So lower potential energy. Than the atomic orbitals. The anti-bonding are the opposite. They are less stable, so they're higher in energy. And so this is pi 2p, sigma 2p, and then we'd say pi star 2p, so that stands for antibonding pi, and sigma star 2p. And it is going to go pi sigma, pi sigma. All right, and now we're going to fill in the electrons. So the number of electrons have to equal. So we're going to have 4 plus 4. So we're going to have 8 electrons. So your number of electrons, if you remember when I taught Lewis structures, we have to be very careful with that. So 2, 4, you always fill lowest to highest. 1, 2, 3, 4, and then 5, 6, 7, 8. So these would each in the pi, each get 1 electron before you have pairing them up. All right, so now we're going to answer some questions about it. And erase this so we can answer questions. And this is for C2. And so my first question, is how many sigma and how many pi bonds? Well, if the antibonding fill up, they completely cancel the bonding. So these are going to cancel each other out. So once we get into the two P's, we're going to cancel out the two S's. Again, you are going to show them to me, just because I'm going to make you show them to me. Yeah, because otherwise what happens, this counts our valence electrons. Carbon was 4 and 4, and people start counting funny and doing funky stuff. So you're going to have to show them. And you're also showing me you understand the idea of the overlap. So we have no electrons in the sigma, so you actually have 0 sigma bonds. The pi bonds, every 2 electrons is a bond. So 1, 2. We have 2 pi bonds. This theory allows you to have pi bonds before sigma bonds. So you actually have that overlap, that donut above and below, and in front and behind, and there's nothing in the middle in this theory, which is really bizarre. But it does work, and it explains a lot of stuff that goes on with technology. So it's pretty cool, and it allows this to happen. All right, there's nothing in the antibonding, so we didn't have to worry about that. We will do some of those in a moment. Para or diamagnetic. This one is again diamagnetic because everything's got a partner. All right, let's see, the hemo. So the highest energy occupied molecular orbital, how high did we go? We got up to the pi 2p. All right, we're gonna do a second one now. Bond order. I'm gonna move bond order up here to the top question. So this was for C2. So bond order, just write BO. All right, the bond order is 2. So you can go through this formula here. Count your bonding electrons, -0, so 4 minus 0 divided by 2, or your sigma and pi bonds must equal your bond order. So it's really easy to do it that way. We're going to expand on this. What if I gave this a negative charge? And that's what this theory allows. It allows us to make things that, could you make this? If you have a bond order that is not 0, it is possible. So we can give it a negative charge, which means it picked up 1 more electron. So it's now going to go in the sigma 2p. So our highest occupied is sigma 2p. That's going to make this paramagnetic. We still have 2 pi bonds. We now have half a sigma bond. because we have one electron. So it is half a sigma bond. And the bond order would be 2.5. So you can just add these two numbers, the pi and the sigma, to get your bond order. Or you can take the number of bonding electrons minus the antibonding, so 5 minus 0, and then divide by 2, and you get 2.5. Okay, we're going to ask I'm going to ask you another question, then we're going to do some practice, and that's really all there is to this. Is which one is stronger of these two? And whenever you're asked this, it has to be asked for the same, like C2 and C2 negative. All right, so the stronger one is the higher bond order. So stronger is higher bond order. So the higher the bond order, the stronger. Which one would be longer? The other one. So higher bond order, that was our bond order little thing. The higher the bond order, the stronger, greater the strength, so stronger and shorter. So if I ask longer, it'd be the other one. All right, I'm going to move us over. And we're on the next page. We're going to do this practice. This is going to be a much shorter video, which is good because I'm getting hungry. All right, Mama Polar Bear is here, but we don't do anything with polar and nonpolar. We do para and diamagnetic, which is what my cow is very paramagnetic. He is sticking to the board. That's called ferromagnetism. So we're going to do Cn and Cn negative. So this is called a heterodiatomic. So two different types of atoms. And we can do it. We're going to keep it simple again. We're just going to stay in the second period of the periodic table. So carbon and nitrogen can overlap. So let's go ahead and draw our picture. So we're going to have our sigma 2s and our sigma star 2s. You guys will always have your notes. But the thing that's interesting is even before when we didn't have notes, this was the thing everybody got. Because once you could draw it, yeah, and it will save you time. And it was an overlap of the 2s. So where you guys have to be careful, you have to make sure you label it fully and correctly. All right. And then we're going to do, so pi, sigma, so those are going to be, it's always pi sigma, and then up here we're going to go pi sigma. And then in the middle, at the layer in the middle, is where my p orbitals will be. And if you're an engineering major or just that kind of person, you can get your ruler out and make these perfectly symmetrical, beautiful pictures. In the outside, these are called my 2p orbitals, and in the center, I have pi subscript 2p, sigma 2p, pi star 2p, and sigma star 2p. All right, so we're going to do carbon on this side, nitrogen on that side, and then I'll put Cn in the middle. Now, the good news is on your worksheet and on your midterm, and even on your homework, you draw this once, use a pen, and then you can use an eraser. Fill in with pencil your electrons, and we just keep counting our electrons. So carbon has 4 and nitrogen has 5, so we're going to have 9 electrons. Now, in the other theory, if we got an odd number, we would have a free radical. And that's why you guys are going to make that healthy change. You're going to say, you know what? I am going to do a healthy change. I'm going to eat 2 apples a day, 3 pieces of fruit a day. So I eat 2 apples a day. Joey, my son, eats 3 apples a day. And then I make, we have berries. I make amazing fruit berries. I'm very blessed. My garden produces all year round. Some birds must have pooped some charred seeds like 10 years ago, and it's wild in my garden. Janae, I sent her a picture of, in the fall, I brought her some, and the chard will get, like, the leaves will get this big, like really big. And so it just keeps all winter long. I had kale last year all winter long, but I heard it. I also had leeks, but I've eaten them all. And so I went and bought some. And so I planted half my garden because the broccoli's amazing, and cauliflower and peas can handle the coldness. Yeah, but it's gonna be beautiful sunny next week, which will be last week for you guys when you watch this. All right, so 4, 1, 2, 3, 4. And over here, we're gonna have 5, 1, 2, 3, 4, 5. So you do have to show me electrons on the outside and then 9 in the center. So 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, so we're gonna answer those questions. And this is where if you have the notes, it's nice because you have this nice little chart. You make your pictures, so the bond order is 2.5. Oh, how could I do that and look so smart? I have 2 pi bonds, because 2 paired electrons, and I have half a sigma bond. We have actually a situation I just did over there. This is definitely paramagnetic, and the highest occupied is the sigma 2p. The next question with the oxygen, we're going to move into the upper ones, and I will show you some stuff that can happen there. To do the stronger, longer, we have to do our second thing, which is CN negative. So look at that amazing thing. You guys can do it too. And so we're going to have one more out here, and if you remember this, maybe one of you does, they like having either all paired or all unpaired. So that extra electron in this case would go here. In the center, it's going to go there. So we now have a bond order of 3. That is the highest bond order you can have in either theory. It means you have a triple bond. That's what the bond order means. A bond order of 2 means a double bond. So we have 1 sigma, which is our pair, and 2, and this is diamagnetic. And again, sigma 2p is the highest occupied. Higher bond order, the CN negative, would win for the stronger, and the longer is the CN. Questions? Oh, we have to write them down. I swear I get to keep going. So you can pause me and keep looking at it and write down what your question would be. And I am going to keep my beautiful chart and just erase the middle. This is where I should use. That's all right. Use this eraser. You know, I'm going to be filling these electrons in again. So really all I have to erase was that. All right. So again, on quizzes, well, on your worksheet, which is your quiz now, you're going to draw one to show me you can draw it. You do one example one, so you would just do it for the CN or the CN negative and just tell me which one it is, and then I'm looking, you can fill in the chart. So we're going to break some of those rules I just taught you. We're going to do OF positive, and OF negative. Because some of you do read the book and you've already said, but. Yes, these are going to break the rule, but I'm going to do it this way first. So we're going to have the oxygen and the fluorine. Oxygen is 6 valence electrons and fluorine is 7. So this is our valence electrons. So they're a group number. And then OF would be 6 plus 7, which is 13. All right, so 6 electrons on this side, 7 electrons on this side, and 13 in the middle. 2, 4, 10, 11, 12, 13. All right, we're going to answer your questions, and then I'm going to show you something that happens. So the bond order. So this is where it gets interesting. There is still 1 sigma bond. There is now only half a pi bond. And the reason is once you start filling in the antibonding, they take away from the bonding. So these 3 cancel out 3 of these. So you have 1 bonding pi electron that is still stable. That gives us a bond order of 1.5. Remember, bond order you can also do where you add 6 minus 3 and divide by 2, and we would get 1.5. But I think it's easier just to add your 1.5, but it's a way you can check yourself. If you get the same answer, you know, I'm good, I'm golden, I did it right. I have an unpaired electron. It does not matter where it is, it's unpaired, it is paramagnetic. The highest occupied is the pi star 2p. And then let's do an OF positive, and then I will show you something that happens. So positive, cats have paws. It's the cat ion. It's like, does that happen? Well, O and F don't happen out there in nature. Mother Nature's really smart. Send love to Mother Nature while you're sending love to everybody, right? All right. Yeah, it can, because we're going to get a bond order. And if you get a bond order of anything other than 0, it can exist. If you fill this whole diagram up, then you get a bond order of 0. Everything's destabilized itself. Then the answer is no, that's not possible. So the noble gases would fill the whole thing up. They can't make a diatomic, but they can do other weird stuff, it turns out, with this theory. So we're going to take one away. And it doesn't really matter which side we take it away from. We're going to take, I want to make sure you took the correct one away, which is that one. So you remember they each, if they're at the same level of energy in the pi star 2p, they each get 1 electron before you start pairing. So our bond order is now 2. We still have our sigma bond. Now, this is a part, whether you like it or not, this is what the answer is. You have 2 half pi bonds. You destabilized half of each of these. You have to have a half bond because it's a paramagnetic again, because you have unpaired. So you do not have 1 pi bond, you have 2 half pi's. It's like 1 point to get that right. All right, the highest occupied is still the pi star 2p. And then let's do the OF negative, would have been 14 electrons. And so we would be here, so 2, 4, 6, 8, 10, 12, 14. Our bond order is a 1 because there is still the sigma. The sigma has not been affected, but the pi is gone. There's no pi. No pi. No apple pie. You're gonna have to eat the apple all by itself. It's like a little squeezy. I'm trying to strengthen my pinky. My pinky doesn't squeeze very well there. All right, so I'm just gonna erase this part so we can get our answers. This is a 0. It is diamagnetic. Everything's paired up. Our highest occupied is still the pi star 2p. We can answer these questions. And don't stop, because there's going to be one more thing that we have to do. Stronger, highest bond order. The strongest is the highest bond order. That is the monkey in the middle. It had the highest bond order. You can make whatever shape. And the longest is going to be the lowest bond order. You can give them a heart. You can do whatever it is that you like. So the piece that's going to happen, and I have no idea why this happens. I have a theory why, and I'm going to share it with you. If you start filling in the pi star 2p, you start, these guys flip. What happens is when you start filling in, my understanding of it, when you start filling in the anti-bonding, it destabilizes the bonding. So probably the sigma stays where it's at, but the pi has been becoming destabilized and it flips above it. And so what you end up with is, you move it down, is the sigma comes first and then the pi. This only happens, the flipping only happens if electrons are in the sigma star 2p. Now, my theory is you have to have at least 2 electrons in there for it to flip, because it has to become destabilized enough that it moves above it. The reason we did the whole chart first is if we go to our 14, 2, 4, 6, 8, 10, 12, 14, and we answer those questions for any of them, nothing changed, because we were up here filling in up here. These are still going to be filled the same. So do you have to flip it? In all honesty, no. You can always show it normal. If it was a question on a test and I asked you to show, it's probably going to make 1 point difference out of however many points I made the class worth. The question that you will see is which ones show the altered molecular orbital, or the flipped. And that would be once we get to 2, 4, 6, 8, 10. So 11 electrons is where the theory says it flips. I don't know how they figured this out. I don't know why that would matter. I think it's just a theory, part of the theory. But it does explain, it does some really cool stuff to it. It does explain magnetism correctly, because the thing that's really cool, I said one more, but is if you did O2, so this explains, MO explains magnetism. And if I can find the video, I'll put the link in there, but magnetism, there's a video where they take liquid oxygen. They take liquid nitrogen and liquid oxygen. And liquid nitrogen, N2 would have 10 electrons. So 2, 4, 6, 8, 10. So it would come out diamagnetic. And so you take liquid nitrogen and they pour it through this super magnet, and it just goes right through because it's diamagnetic. It has no attraction. But then they take liquid oxygen, which has 12 electrons. And 12 electrons means it's going to fill in up here, and it's going to be paramagnetic. And they take liquid oxygen, and they dump it into this magnet, and the liquid just stops moving. It doesn't pour through. It's stuck in between the magnet, and so you can see this liquid there. And so the molecular orbital theory correctly explains magnetism. The other theory, the Vesper theory that we worked with, the valence bond theory, the oxygens would have a double bond. That's 12 electrons, and so you can't predict magnetism. All right, well, that was bond theory, and many blessings to you all this week. I will see you soon when we do the organic chem lab.